Hello students, we are going to continue our discussion on atoms. In this lecture we will talk about what isotopes are, and rounding our discussion of the atoms, we're talking about the electrons and how the electrons dictate a lot of the trends we find in the periodic table. To start our discussion of isotopes, let's take a look at the simplest atom, the hydrogen atom. As depicted in my cartoon here of the hydrogen atom, you can see that there is one electron and one proton in the nucleus. But it turns out there are other hydrogen atoms that not only have one electron, one proton, but also in addition one neutron. Now remember that an element is defined by the number of protons it has. So this atom, it turns out, is still considered a hydrogen atom. This is essentially what is known as an isotope. So for the element of hydrogen, we now know of two isotopes. The first one is still your simple hydrogen, whereas this one is a new isotope. And in particular, for hydrogen, this isotope is called deuterium. Hydrogen has more than one isotope. It has a third isotope called tritium. And in the tritium isotope, there is two neutrons. And so from this example, we can see that isotopes are simply atoms of the same element, but they differ in the number of neutrons they have. So how do we write the symbol for the isotopes? The symbol for isotopes is simply written with the chemical symbol and a subscript and a superscript. The subscript represents the proton number or the atomic number, whereas the superscript represents the total number of proton and neutron. Remember what that number was called in our previous lecture? Good job if you remember that that is called the mass number. So in the regular hydrogen atom, we see that the atomic number is 1 and the mass number is also 1 because it only has a proton and no neutron. Whereas in the deuterium isotope, the mass number is now 2 because it has 1 proton and 1 neutron. 1 plus 1 is 2. The atomic number has not changed, so the subscript is still 1. What do you imagine tritium symbol looks like? The tritium symbol would look exactly like the other, except the mass number of 3 because of the 2 neutrons and the 1 proton. Let's take a look at another element to flesh out this idea even further. Let's take a look at magnesium. Magnesium is atomic number 12. That is why the subscript for the symbol will always be 12. Now the superscript will always be different depending on the isotope. Written here we can see 3 different isotopes of magnesium. One with 24, one with 25, and the other with 26 as its mass number. And as a review, let's count the number of neutrons from its mass number. Remember that the mass number minus your atomic number, or the mass number minus the number of protons you have, is the number of neutrons you have. So in this case, 24 is your mass number, minus 12 will give you 12. So there are 12 neutrons in magnesium 24, and 13 neutrons in magnesium 25, and 14 neutrons in magnesium 26. Now, as I have mentioned, the subscript in this symbol is quite redundant. Because if you are a magnesium atom, you must be an atom that has atomic number 12. That's the definition. So that 12 becomes redundant, so we can write the symbol for the isotope simply with the mass number on top. Another way of writing this is to just put a dash between the symbol and the number. So you can say it's magnesium-24. In our spoken language, we would call this simply magnesium-24 versus magnesium-25 and magnesium-26. Now there is one more number related to atoms that we have not discussed, and that number is called the atomic mass. Now the atomic mass is usually found as a number below the chemical symbol in the tile of the periodic table. Now what is that atomic mass? So for example, the atomic mass of magnesium is 24.31 AMU. But again, we just said that the mass number of the different isotopes of magnesium are 24, 25, and 26, meaning that there are some atoms that are 24 AMU, some that are 25 AMU, and some that are 26 AMU. So why is it that the atomic mass is 24.31? Of the 3 numbers I cited, that's not one of them. So as it turns out, the atomic mass is actually the average of all of the isotopes' mass. And this is a weighted average. A weighted average takes into account the natural abundance or the natural occurrence of a particular isotope. So for example, magnesium-24 occurs 78.70% in nature, whereas magnesium-25 only occurs about 10%, and magnesium-26 only occurs about 11%. So if you take the average of all this, it does make sense that the average magnesium atom would weigh about 24 AMU, because that is the majority of the isotopes. Let's use these lemons as an analogy to help us understand atomic mass and what weighted average is. Imagine you have 4 lemons, and 3 of those lemons are 3 ounces, while there is a smaller lemon that is only 2 ounces. If I ask you what is then the average weight of the lemons, how would you calculate that? Mathematically, you would have added up all the weights and then divided by the total number of lemons you have. So that will be 3 ounce plus 3 ounce plus 3 ounce plus 2 ounce divided by 4, giving you 2.75 ounce. Meaning, if you were to distribute the weight out evenly between the lemons, each one would weigh about 2.75 ounce. Much like the atomic mass, this number is not an actual weight of any of the lemons, right? There are no lemons that are actually 2.75 ounces. They are either 3 or 2 ounces. But rather, this is the weighted average. And this weighted average does make sense. 2.75 ounce is closer to 3 ounce than it is to 2 ounce, because there are more lemons that are 3 ounces than there are lemons that are only 2 ounces. There's another mathematical method to calculate the weighted average that doesn't involve such tedious addition. Let's say you had 100 lemons instead, and 99 of those lemons are 3 ounces and 1 of those lemons are 2 ounces. Would you add 3 plus 3 plus 3, 99 times, and then plus 2? That's too tedious, right? So instead, what we can do is use percentages using the natural abundance. We can say that among these lemons, there are 75% of them that are 3 ounces, 3 out of 4, and 25 that are only 2 ounces, 1 out of 4. So if we take 75% times 3 ounce and you add that mass with 25% times 2 ounce, you should get the same answer. And remember how to write percentage. You can say 75 over 100 times 3 ounce, or in your calculator, you can also put 0.75 times 3 ounce. And indeed, when you do it in this fashion, you can try to prove it to yourself that you do get 2.75 ounce. This is just a quicker way to get the weighted average. So again, going back to our elements, the atomic mass is not the mass of any actual atom. So for example, you cannot find a magnesium atom that is exactly 24.31 AMU. It is just the average of all of the atoms that we know of. Let us see if we can take this math and apply it to getting the atomic mass of chlorine. It turns out chlorine has 2 main isotopes, chlorine-35 and chlorine-37. Chlorine-35 exists 75.76% of the time, whereas chlorine-37 exists 24.24% of the time. To get its atomic mass, we need to get the average weight. And to calculate for the average weight, we can use the formula mentioned in the previous slide. So you take 75.76%, multiply it by the weight of the chlorine-35 isotope, which is 34.97. Okay, take that, and then add it to the mass of 24.24% of the chlorine-37 isotope, which has a mass of 36.97. Add those two masses together, and you should get 35.45 AMU, which turns out correctly to be the atomic mass of chlorine. So if you try this on your own, this math actually isn't that scary. Time for a checkpoint. The question reads, the atomic mass of carbon is 12.01 AMU. Which of the following statement is true about carbon-12 and carbon-13, the 2 main isotopes of carbon? Pause this video to do this checkpoint. Great, hopefully you said the answer was A. Carbon-12 is more naturally abundant than carbon-13. We know this is true because the atomic mass of carbon is 12.01, which is very close to carbon-12, which you would imagine to have a mass of about 12 AMU, whereas carbon-13 would have the mass of about 13. Answer B is incorrect because carbon-12 has a mass number of 12, which is less than 13. Answer C is incorrect because all carbon isotopes will have 6 protons only. If you have 7 protons, you are no longer carbon, you would be nitrogen instead. And finally, answer D is incorrect because 12 and 13 here does not mean the number of neutrons, it is actually the mass number. So that rounds out our discussion about the subatomic particles that exist within the nucleus. And for the rest of this lecture, let's talk about the subatomic particle that lives on the outside of the nucleus. Those are the electrons. And it turns out we will mainly focus on the electron for the rest of the semester, except in one chapter when we talk about nuclear chemistry. The rest of chemistry really is dictated by electrons. So electrons turn out to be very important. Before we talk about the chemistry and properties that are the results of electron, let's talk about electron configuration. In other words, where they live. Previously, we vaguely said that electrons are located on the outside of the nucleus. Specifically though, electrons live in discrete energy levels, or we can call them layers, just like layers of an onion. And in each layer, there is a maximum amount of electrons that it can contain. For example, in level 1, you can have only 2 electrons. In level 2, or in layer 2, you can have 8 electrons as a maximum. Then in layer 3, you can have another 8 electrons as a maximum. Now, beyond level 3, it gets a little bit more complicated, and we will not go there in this course. And as it turns out, the higher you go, the higher the energy level is. An analogy to this is going to a Las Vegas hotel. The higher the floor that your room is in, the more money it will cost. And as it turns out, electrons are just like us. They want to occupy the lowest energy level possible, aka the cheapest hotel room. So we can actually describe which level electrons exist in. This is called electron arrangement. I will go through a couple of elements to show you what I mean. Let's start with hydrogen. Hydrogen, element number 1, has 1 proton and therefore must also have 1 electron, right? And because it has only 1 electron, that electron can stay in the lowest energy level, the first energy level. Moving on over to helium, how many electrons does helium have? It is atomic number 2, 2 protons, therefore 2 electrons. Having 2 electrons, it can leave both of those electrons in the first energy level because, as we said previously, the first energy level can contain a maximum of 2 electrons. Which means when we go to lithium, which has 3 electrons, that last electron cannot fit in the first level anymore. So as a consequence, that last electron is bumped up to the next energy level, in level 2. So to write the electron arrangement for lithium, we write 2, 1. Moving on next to its neighbor, for beryllium, it has 4 electrons. 2 electrons will live in the first energy level, and the last 2 electrons will have to be on the second energy level. So the electron arrangement for beryllium would be 2, 2. Boron, same thing. It has now 5 electrons. 2 can be in the first electron level, but the 3 last ones have to be on the second level. So its arrangement is 2, 3. Now I can move on a little bit faster, right? So carbon would be 2, 4. Nitrogen would be 2, 5. Oxygen would be 2, 6. Fluorine would be 2, 7. Neon would be 2, 8. Notice what happens when every time we reach at the end of the periodic table. Just like in helium was the end of the periodic table in group 8A, when you reach at the end of the periodic table, you have reached a maximum number of electrons possibly fit in that energy level. Because, as stated in the previous slide, the second level can only fit 8 electrons. In this case, at neon, we already have 8 electrons on the second energy level. So when we move to the next element, element 11, sodium, it would have 1 extra electron, and that 1 extra electron now will have to move on to the third energy level, given the electron arrangement of sodium as 2, 8, 1. Okay, so at this point, if I were to tell you that there's an element who has an electron arrangement of 2, 8, 4, what element would you say that would be? It would look something like this, and it would be silicon. Very good. Because silicon, element number 14 right here, because it is in the third row, we know that its first and second row are completely full. So we say 2, comma, 8. And now that it is in the third row, we can ask ourselves how many electrons it has in the third row. And that's 1, 2, 3, 4. 4 electrons on the third shell. So that's 2, comma, 8, comma, 4. So this may seem trivial to us, but as I mentioned, this will dictate a lot of the properties of elements and the way they interact with one another in a chemical reaction. And this knowledge of the electron was first hinted by works done by scientists in the 19th century when they looked at different elements and something called its atomic spectrum, which is like the fingerprint of each element. Now, to understand atomic spectroscopy a little bit, we have to backtrack and take a look at light. Light, or otherwise known as electromagnetic radiation, is a form of energy that actually moves as waves. So I'm going to show you two waves. Try to notice the difference between these two waves and then also what similarities they have in common. Did you catch it? Let me show you that one more time. Notice this time that the wave starts and ends at the same place at the same time. What does that tell you about its speed? And also, try to see what's different about them. Does one seem a little bit more erratic? That's right. So what they do have in common is that light will always travel at the same speed. We call that, as you may know, the speed of light. So they start and end at the same place and at the same time because they have the same speed. But their journey is quite different. One, you may say, is very energetic or very chaotic, where one is very smooth and low in energy, right? One thing you can measure about waves is something called the wavelength. To measure the wavelength, you just measure the distance between a point on the wave and another point where it resembles. So for example, if these are two peaks, they're very similar to each other. If we measure that, we can measure its wavelength, or we can measure the troughs at the bottom. In the red wave, the wavelength is longer than in the purple wave. A long wavelength corresponds with low energy, while the short wavelength corresponds with high energy. You can almost imagine this literally as waves in an ocean and you are a boat in that ocean. Imagine you here and the waves are coming at a higher frequency. That would be a stormier sea than if you were a boat and the waves are coming much more slowly. So you can imagine this wave is higher in energy, whereas this wave is lower in energy. And so each wave will have its associated wavelength and frequency and its associated energy. And when it reaches our eyes, we interpret it as different colors. So if it is a long wavelength, let's say 700 nanometers, we see it as red. Or if it's a short wavelength at 400 nanometers, we see it as violet. Or if it's a wavelength in between about 550 nanometer, we interpret that in our brain as green. And so with each wavelength, we can see different colors. And actually, it turns out there are more wavelengths than this, wavelengths that we cannot see. The waves that we can see actually are not that many. If you see the whole spectrum of light, we can only see a small part in that spectrum. If the waves have shorter wavelengths, we cannot see it beyond 400 nanometers. For example, beyond violet is ultraviolet. We cannot see this kind of light, but it still affects us. For example, we have to wear sunblock and sunglasses to block the ultraviolet radiation from the sun. Even beyond ultraviolet, we have things like X-rays and gamma rays, which are very high in energy. On the opposite end of the spectrum, we have lights that are lower in energy, which means longer in wavelength. For example, beyond red, we can see infrared, which is basically heat. And beyond that, we have microwaves, which are the wavelengths that are corresponding to things like your cell phone signals, microwave to heat up your food, and satellite. And beyond microwave, even longer wavelengths are things like radio waves. Alright, so at this point, let's have a pop quiz. What's the correlation between a wavelength versus frequency? Okay, right? So long wavelength would have low frequency, whereas short wavelength, really fast, right, will have very high frequency. So again, what does all of this have to do with electron arrangement? Well, we have one more piece of information to talk about before we have an understanding of what gave scientists a glimpse into electron arrangement, and that is a prism. A prism can split up light, and this fact is something that is known all the way back to the Roman times, that when you shine light through a prism, like this light from the sunshine, it will split up into its component, making what we know as the rainbow. Much like how we actually see the rainbow, that's because the raindrops acts as a prism to split up the colors in the sunshine, giving us an actual rainbow. Now, if you were to graph that rainbow into a chart, you will have that spectrum that we have seen earlier. And so scientists in the mid-19th century, notably Gustav Kirchhoff and Robert Bunsen, made a series of experiments where they burned different elements, and as the light of those elements are put through a prism, they spit out spectrums, and each of these spectrums are unique to every substance. And again, if we take barium and burn it, it will have a greenish light, and you take that light and you put it through a prism, splitting the component of that light that's given out by the barium, it actually looks like this. Where as opposed to a continuum of colors, as you see from a visible light giving that rainbow, it actually has discrete lines between dark spaces. Each element they burn will have a particular pattern, and this pattern is called its atomic spectrum, which is like the atom's fingerprint. And so with a little bit more research, we now understand this phenomenon. It turns out when you give a substance energy, and giving energy can mean like you burn something or you turn on the electric current. So whatever form of energy it has, when you give a substance energy, the electrons are usually in their lower state energy, gets excited and move and jump on to a higher energy level. And as you may know, after every high follows a low. And so as the electron falls back down to its original energy level, it releases the same amount of energy that it has absorbed. And so if it absorbs a high amount of energy, it will release a high amount of energy. And in this case, that energy amount is a red light. If, however, it was excited to jump to a higher energy level, when it comes down, it will release a higher energy, for example, a green wavelength instead. And so when you burn those elements, you are exciting the electrons, and they will go back down, and as they go back down to their former energy level, they will release light, much like how fireworks works. And so because the atomic spectrum is not continuous like light, but very discrete lines, we know that electrons must be jumping from one state to another state in a very discrete manner. And so from this conclusion and further research in the field that is now known as quantum mechanics, we now know that electrons live in layers, and these layers are called electron shells. They are designated with what is known as a quantum principal number n, much like a room is designated with the floor number. For example, the first energy level is called n equals 1, the second level is n equals 2, the third level is n equals 3, so on and so forth. And that these energy levels are quite discrete. A technical term for it is quantized, meaning there is no n equals 1.5. There is no 1.5 level. You are either on the first floor or on the second floor. Let's have a checkpoint. Can you write the electron configuration for an atom with 13 protons and 14 neutrons? Hopefully you recognize that to write the electron configuration, you only need to know how many electrons an atom has. So 14 neutrons is a number that is irrelevant to this problem. But knowing that it has 13 protons and it's a neutral atom tells you that it also has 13 electrons. Looking at our periodic table, we know that must be aluminum, and therefore, to write the electron configuration, we surpassed the first and the second level, so that's 2 and 8, and now it has 3 electrons on the third level, 1, 2, and 3. So the answer is 2, 8, 3, which is C. Alright, so we spent a lot of time talking about electron arrangement and how electron arrangement was eventually discovered because, as I have mentioned, electron arrangement is very important in dictating the characteristics of the elements. Let's take a look again at the electron arrangement of overall of some elements. It is in this table organized by group number. So the first trend is related to group number. Let's focus in on group 1A first. Group 1A here, let's take a look at three elements: lithium, sodium, and potassium. Again, lithium would have electron arrangement of 2, 1, whereas sodium would get 2, 8, 1, and potassium is 2, 8, 8, 1. Notice a pattern? Yes, they all end in 1. The last number, the outermost layer, is all the same. And it's the same, and it corresponds to the group number. So group 1A atoms all have 1 electron on its outermost shell. Another example is group 7A, the halogens: fluorine, chlorine, bromine. They are in group 7A, so they all have 7 electrons in its outermost shell. So the first trend I want to talk about is that elements in the same group will have the same number of what is called the valence electrons. So valence electrons are the electrons that exist on the outermost shell. This is the first time we are introduced to the concept of the valence shell, and we'll come back again and again when we talk about the chemistry of reactions and the properties of elements. So let's start that with talking about some trends in the periodic table that are dictated by valence electrons. The first of those trends is atomic size. Let's first take a look at three atoms: hydrogen, lithium, and sodium. They are all in the same group. Hydrogen has 1 electron, and that 1 electron is in its first level, whereas lithium has 2 in the first level and 1 electron on the outermost level. One way of thinking about the atomic size, since we can imagine atoms as spheres, is to think about the radius of the atom. And the radius of the atom is the distance between the nucleus and the outermost electron. So it does make sense that as you go from electrons in the first shell to the second shell, that your radius is increasing. So far, the trend we see is as you go down the periodic table, every single time you move on to a new period, you have a new shell, right? This is the first shell, the second shell, the third shell, the fourth shell. So it makes sense that every time you go down the periodic table, your radius, your atomic size should be increasing. And indeed, that is the pattern that we see in atomic size, that the atomic size will increase as you go down the periodic table. What about if you were going left and right in the periodic table? As an example, if I was going from lithium to neon, going from left to right, I can't use the previous argument that I'm going into a different shell, so I'm going to increase or decrease. Since I'm staying in the same row, I am in the same electron shell. So to understand this trend, we have to remind ourselves of the attraction between the positive nucleus and the negative electrons. Remember that when we are going from left to right, from lithium with 3 protons and 3 electrons to neon with 10 protons and 10 electrons, we not only increase the amount of protons and electrons, but we increase the amount of positive charge and amount of negative charge. So if you have more things that are very attracted to each other, how do you think it will affect the size? That's right, the size will contract as the positive is pulling the electrons in because it's a greater positive charge and there's more electrons, so the attraction is increasing. So indeed, that's the trend in atomic size, that as you go from left to right on the periodic table, you are decreasing in atomic size. So with that, it gives us our overall trend in atomic size. As you go from top to bottom, you are increasing, but left to right, you are decreasing in atomic size. So if I were to ask you between boron and fluorine, which is the larger atom, you would say boron, correct? Because boron is left of fluorine. As you go from left to right, it decreases. What about oxygen and sulfur? Hopefully you said sulfur was a larger atom because sulfur is below oxygen. What if I ask you about beryllium and krypton? Take a moment to locate beryllium and krypton on your periodic table. Which one would be bigger? If you're scratching your head, that's a good thing because this is a trick question. This question cannot be answered with the trend that we just looked at. Because this is beryllium and this is krypton. According to our trend, krypton is to the right of beryllium, so it should be smaller than beryllium. But according to another trend, krypton is below beryllium, It's on the fourth row instead of on the second row, so it should be bigger. So these trends have opposing effect. Because of that, you cannot answer this question. What about neon and chlorine? Neon is to the right of chlorine, but also above chlorine. So neon is going to be smaller, so our answer is indeed chlorine is your bigger atom. The second trend affected by electrons and related to atomic size is something called ionization energy. And ionization energy is the energy that is required to remove the valence electrons from an atom. To imagine this removal, think about this atom, the helium, versus this atom, the lithium. As it turns out, since this valence electron is closer to its nucleus, it is going to be more tightly held than this electron, which is farther away from its nucleus. So the ionization energy trend is that as you go down the periodic table, the valence electron will be farther and farther away because the atomic size is also increasing. Your ionization energy will also decrease. That is correct. The ionization energy trend is opposite that of the trend of the size of the atom. As you go from left to right, the ionization energy increases because the atoms are getting smaller and smaller. As you go from top to bottom, the ionization energy decreases because the atoms are getting bigger and bigger, the electrons are getting farther and farther away from the nucleus having less of a strong grip on that electron since it is so far away. Now another trend related to ionization energy is called metallic character. Metallic character is basically the ability to lose electrons. It turns out metals love to lose electrons. So the more you are able to lose an electron, the more metallic you are. So think about the trends we just talked about, ionization energy. So if you have a low ionization energy, you have a better ability to lose that electron, right? So this trend is opposite that of ionization energy. As you go down the list, the ionization energy decreases. So as the ionization energy decreases, if you require less energy to remove that electron, you are more likely to remove that electron. So its metallic character will increase. Same thing, as you go from left to right, the metallic character will decrease. So this trend is opposite that of ionization energy, but the same trend as the atom size. As the atom gets bigger, it becomes more metallic. As the atom gets smaller, it becomes less metallic. All right, time for a checkpoint. Which of the following elements has the highest ionization energy? Sodium, magnesium, sulfur, or oxygen? Think about it. So I only like to memorize one trend, and that trend is atom size. So I know that the size of atom will increase down and decrease to the right. And I know that the ionization energy is opposite of that of the atom size. So in order to have the highest ionization energy, you must be the smallest atom. So in this case, oxygen is my smallest atom because it is most to the right and most to the top. And I would be correct. D, answer is oxygen. Alright, so by the end of this lecture, we have rounded out the chapter talking about elements and atoms. But particularly in this lecture, we talked about how to determine the number of subatomic particles of isotopes of an element and to calculate the atomic mass. We also talked about the electron arrangement and how to write the electron arrangement for different elements. And lastly, using the electron arrangement, we talked about the trends we see in the periodic table.